Welcome to Fractal Universe. To go to the main menu, press button A on your remote controller. To generate your own fractals, press button B. At any time, if you wish to quit the section you are viewing, press button B to return to the previous menu. Fractals are mathematical structures of immense beauty and infinite complexity. However closely you examine a fractal, there is always more detail to be seen. Many fractals are self-similar, such as the Julia fractal shown here. Look closely at one of the small curls. The shape is very similar to the larger one, although not identical. Further magnification reveals that even the smallest portion of the original picture is as complex as the original. However far you magnify, you will never reach the end of a fractal. When the first fractals were discovered by mathematicians in the 19th century, they were mostly ignored, regarded as mathematical curios. The problem was that mathematicians couldn't explain their properties. The mathematician Sierpinski discovered one famous fractal, now called the Sierpinski triangle, although the term fractal was not used until much later. Take a perfectly ordinary triangle. The triangle is one of the most stable and most easily defined objects in mathematics. The area is half the length times height, and the circumference is the sum of the length of the three sides. Divide the triangle into 4 equal triangles and remove the internal triangle. You are now left with 3 smaller triangles. Now divide up each of these as before and remove the central portion from each. Now there are 9 triangles. The area is now substantially less than before. Repeat the process indefinitely and you are left with a ghost image made up of lines. Sierpinski knew there was something odd about this shape. Although it was the same overall size as the original triangle, it was made up of an infinite number of lines and it had no area at all. Many years later, Mandelbrot looked at this shape and asked, "How many dimensions does it have?" The triangle plainly has 2 dimensions. It has length and height, and it has an area. The Sierpinski triangle has a length and a height, yet it has no area. Mandelbrot found that the Sierpinski triangle had more than 1 dimension, but less than 2. It had a fractional dimension. Mandelbrot soon discovered many other fractals, and realized that fractals were present in nature too. Mountains, clouds, plants, waves, snowflakes, trees. Almost everything in nature is fractal. The closer you look, the more complex the object becomes. Simple mathematical formulae can mimic nature by producing realistic ferns, mountains, and clouds. Mandelbrot went on to discover a method of working out the fractional or fractal dimension of such objects. Fractals can be roughly divided into 2 types. The first type are called repetitively generated. These involve a pattern being repeated indefinitely. Repetitively generated fractals have an initiator and a generator. If we take the Sierpinski fractal as an example, the initiator is a triangle and the generator is a triangle with the center portion removed. The generator is applied to the initiator. This will cut out the center of the triangle. Then the generator is applied again to each of the remaining portions. After 3 or 4 generations or iterations, you are left with an image of the Sierpinski triangle. The other main type of mathematical fractal are called complex plane fractals. They are all plotted on the complex plane using complex numbers. Complex numbers aren't that complex, really. The term is used because each number has 2 parts. Here is a picture of the complex plane. Think of it like a map. Each point on the plane will have 2 reference numbers, one from the scale going across called the x number or real number, the one from the scale going down called the y or imaginary number. Don't worry about these terms as they are not important from our point of view. We give them here so you can understand references mathematicians make to the real and imaginary axis. This point here represents a complex number of 0, 0. It is at position 0 along the bottom and 0 up the side. This point represents the complex number minus 0.2, 0.5. You can see that we can choose a point anywhere and give it a complex number position even though it may involve several decimal points. In fact, there are an infinite number of choices. Let's draw one type of complex plane fractal, a Julia set. For this we use the Julia formula, and first of all plot what will happen to one dot, say the top left-hand one. We use Z as the complex number representing that dot, and C as the point on the plane for which we plot the Julia set. Off we go and cycle through the formula, putting the answer back into the beginning for a set number of times or iterations. The number of iterations is not fixed, but the more times we do it, the more detailed the picture will be and the longer it will take to generate. We then move on and plot the next dot on the screen using Z as the dot's address and keeping C as the point for which we want to see that Julia. Once we have reached the end of the iteration for each dot, we look to see what number we are left with. Some will be very high and going off towards infinity. We will leave these colored green. They are not in the Julia set we are plotting. Other points will give values that stay low, and we will color these black. They are in the set. Let's plot the Julia set for the complex number 0, 0. The Julia plot for 0, 0 gives us a black circle. Let's try another point, say 0.5, 0.6. This has produced a far more complex Julia pattern. To make the pictures more interesting, instead of plotting the dots outside the set in just one color, we can paint them different colors according to how fast they move out of our range as they are being iterated. It has been mathematically proven that if the number rises above 2, it will eventually reach infinity. If therefore we stop the iteration when the answer reaches 2, and then see how many times we had to go through the formula to get there, this can act as an index as to how we color the dot. If it takes many iterations to reach 2, then we color it one color. If it takes a few, we color it differently. Here is the same Julia plotted in color. You can see Julias plotted from all over the plane and in many different colors in our art gallery. In 1979, after plotting several Julia sets on his computer and printing them out, Mandelbrot decided to alter the method of applying the formula. Instead of using the position of each dot as the starting value for Z, he started with Z equals 0 and used the position of the dot he was plotting as the constant C. When plotted, we see the now familiar Mandelbrot set. Because of the way the set is plotted, there can only be one Mandelbrot set, unlike Julia's, of which there is an infinite number. But the Mandelbrot set is one of the most complicated mathematical structures known. By zooming in and plotting different areas with very fine precision, some startlingly beautiful pictures can be found. The depths of it will never be fully explored, as it extends to infinity. There are many different patterns to be found in the Mandelbrot set. This area is known as the seahorse tail. We don't need to stay in the set color shown. Here is the same picture, plotted with different colors. Each time we zoom in further, the area of the complex plane we are looking at is magnified. This means that we need to use more and more accurate mathematics. We also need to increase the number of iterations in order to obtain detailed pictures. At very high magnifications like this, it may take several hours or even days to fill the screen. We have plotted a large selection of such high magnification fractals for you to see. They are included in our art gallery. Ever since the dawn of modern science in the ancient civilizations of Greece and the Middle East, people have tried to explain the universe in simple terms. The discovery of geometry in ancient Greece led philosophers such as Pythagoras to suggest that there was some natural mathematical order that described the universe. Pythagoras discovered the 5 perfect solids. He found natural counterparts to his perfect solids in the mineral world. However, while these crystals replicated the simple beauty of geometry, perfect crystals are rare. Pythagoras must at some time have picked up a pebble and wondered how its irregular, rough surface could fit into his geometric universe. The fall of the classical civilizations and the rise of religious bigotry during the Dark Ages prevented the advancement of science for over 1500 years. Johann Kepler was born in 1571. From his youth he was fascinated with the stars. He devoted his life to the search for a natural geometrical order that described the position of the 6 known planets in the solar system. Whilst teaching mathematics, he discovered that by inscribing an equilateral triangle inside a circle representing the orbit of Saturn, another circle drawn inside the triangle represented the orbit of Jupiter. Kepler worked for the rest of his life trying to fit the orbits of the planets in between the 5 Pythagorean perfect solids. He drew diagrams and built models of his vision of the universe as he saw it. Classical thought in Kepler's time talked of the planets as points of light inscribed on massive crystal spheres. 2,000 years previously, Pythagoras had talked of the harmony of the spheres, thinking that the orbits of the planets were in some way related to the geometric progression of the notes on a musical scale. Kepler himself said, "Geometry provided God with a model for the creation. Geometry is God himself." As time passed, Kepler became increasingly frustrated with the fact that, however hard he tried, he could not get the planets to match his model exactly. He thought that his limited astronomical data collected from a time before the telescope must be incorrect. Eventually he obtained the observations of the Danish astronomer Tycho Brahe. From Kepler's point of view, this made things worse. Not only did the new data not fit his geometrical model of the universe, it also proved that the orbits of the planets were not, as previously assumed, circular, but were elliptical. Kepler was devastated. The universe could not be explained purely in terms of geometry. The fact that he had discovered one of the most important discoveries in astronomy in 2,000 years was little consolation. Geometry had failed him. Isaac Newton, in his investigations into gravity, carried on with Kepler's work on the motion of the planets. While studying this, he came across a problem. With 2 planets of the same mass, working the gravitational attraction between them was easy. At any point, the gravitational field would attract an object to one of the 2 planets. The area of gravitational attraction for each planet is easily defined. With 3 or more planets, it suddenly becomes more complex. Using approximations, Newton was able to prove that in the areas immediately around each planet, a point would be attracted to that planet, but in the space between the 3 planets, there appeared to be a chaotic region, where the final outcome could not be predicted. With modern computers, we can calculate the appearance of these chaotic zones, and we find infinitely complex patterns in the gravitational fields. Helge von Koch was a Swedish mathematician. In 1904, he described a mathematical structure that he called his coastline. Koch realized when he discovered this structure that it had some unusual properties. Firstly, the line is infinitely long. Despite this, the line fits into a finite space. The triangle can be drawn round the shape, a finite geometrical shape, with an infinite complex line inside it. Secondly, at no time does one portion of the coastline meet another. Thirdly, by magnifying a small portion of the shape, we can see that it is identical to the whole shape. It is self-similar. Helge von Koch and other mathematicians of the 19th and early 20th centuries described several similar shapes. fantastic mathematical curios with which to amuse their fellow mathematicians. But the true significance of their discoveries was not to be known in their lifetimes. In 1914, two French mathematicians, Gaston Julia and Pierre Fatou, were investigating the properties of iterative formulae. An iterative formula is simply a formula where the result is put back through the formula several times until a final result is obtained or until infinity is reached. The particular formula that Julia was interested in was very simple. Take a number, square it, and add a constant value. Now take this value, square it, and add the constant to it again, and so on. Julia was surprised to find that the shapes he was getting were irregular. Everything had to be meticulously calculated by hand, and although he saw fragments of worlds and spirals, it is only with the advent of modern computers that the true beauty of these images can be displayed. But 1914 was not the best time to be studying mathematics in Paris. Julia found little interest in his discoveries whilst Europe was in the midst of the most destructive war in its history. Benoit Mandelbrot was born in Poland in 1924. His family was Jewish, his father worked in the clothing trade, and his mother was a dentist. In 1936, sensing the coming of the Nazi threat, the Mandelbrot family moved to Paris, where the young Benoit came under the influence of his mathematician uncle. When Hitler advanced into France, the family broke up, and Benoit spent most of the war years living in Toul, a town in the central France. He had little formal schooling, but was guided by teachers often themselves anxious to avoid the attention of the Nazis. He was never in one place for long. After the war, Benoit returned to Paris and passed the entrance examination for the prestigious École Polytechnique. One of his teachers was an elderly French mathematician, Gaston Julia. In 1954, Mandelbrot emigrated to the USA, where he began to work at IBM's research department. Thereafter he followed various careers, mostly as a lecturer, teaching engineering, economics, physiology, and mathematics. In none of these was he regarded very highly by his colleagues. They did not like his informal and unorthodox methods. In the early 1970s, Mandelbrot started thinking about Koch's work, in particular his coastline. He thought about the coastline of Great Britain. Mandelbrot wondered, how long is the coast of Great Britain? He soon realized that the length of the coast depends on the length of your ruler. The island viewed from space can be measured approximately. A survey team measuring at 100-meter intervals around the coast will give a different, higher value. Crawling around the coast with a 6-inch rule will give a higher value still. A snail traversing every small pebble would, if it could live long enough and give an answer, arrive at a very much larger result. Rather than settling down to an approximate value for the length of the coastline, Mandelbrot found that the smaller the lines used to measure the coastline, the larger the value he got. The coastline of Britain was infinitely long. Mandelbrot looked again at the Sierpinski triangle. Here was a finite triangle, one of the most stable forms in mathematics. A triangle is removed from the center to leave 3 triangles. From each of these, the center portion is removed, and so on, ad infinitum. Mandelbrot tackled the subject from a different point of view. He began to think in terms of dimensions. In mathematical terms, a dot has no dimensions. A straight line 1, a square has 2, and a cube has 3. But what about the Sierpinski triangle? How many dimensions does this structure have? Not 0, not 1, not completely 2 either, because it contains 0 area. It appeared to be somewhere in between 1 and 2. Mandelbrot could immediately see that he was on the right lines. The idea was a brilliant solution, and he went on to define ways of working out the dimensions of all such figures. They all had fractional dimensions. One day in 1975, while helping his son with his Latin homework, he was struck by the Latin root fractors, leading to such English words as fracture and fraction. He invented the word fractal to cover his new geometry, and another branch of mathematics was born. In the late 70s, Mandelbrot remembered his old professor Gaston Julia and his formula. He began plotting Julia sets using a computer at Harvard and outputting to an old printer. He became fascinated with the results, which were far less detailed than those seen here. One day, in 1979, he slightly altered the way they were generated, and saw the first unclear outlines of the set that bears his name today. He rushed to the mainframe computer at IBM to confirm his discovery, and saw the Mandelbrot set being generated for the very first time. Even the mainframe computer at that time was not able to produce it to the same level of detail you see here. There are an infinite number of different Julia patterns, but only one Mandelbrot set. Mandelbrot discovered his set was a guide to all the Julia patterns. Every point on the Mandelbrot picture can be used as the constant value for the Julia formula. All the points within the black area of the Mandelbrot produce solid Julias. Points outside of it produce fragmented Julias. Points near the edge of the Mandelbrot set produce the most complex and often the most beautiful Julias, like this one. Following the publication of Mandelbrot's book, The Fractal Geometry of Nature, in which he outlined fractal theory, many books and articles have been written about fractals, and thousands of pictures have been published. Fractals have found practical uses too, with their ability to create realistic landscape pictures. Science fiction films have used fractals to create whole alien planets. NASA has used similar technology to produce animated movies of flights across Mars and Venus from data returned by planetary probes. Michael Barnsley, author of the book Fractals Everywhere, has invented a system to compress video data to a fraction of its original size, based on his IFS self-similar fractal formula. This could allow video phones and full motion video from a compact disc to become a reality in the very near future. We begin our journey with a view of the whole Mandelbrot set. The box shows us the area we will magnify for the next picture. At greater magnification, we can see greater detail than before. We will place our box on an apparently insignificant three-way junction. On magnification, we see that there are several miniature copies of the Mandelbrot set dotted around. There are, in fact, an infinite number of these miniature copies, each of them slightly different. We carry on and zoom into the center of the junction. Again, we see more miniature Mandelbrots, which, although tiny, are as complex as the entire set. Each of these small Mandelbrots is connected by thin filaments. Let's have a closer look at one of these miniatures. Note that this Mandelbrot is pointing in a different direction to the main set. In again, deeper and deeper to view the heart of this Mandelbrot. Our magnification is so great now that we are losing definition and accuracy. We can redefine the accuracy by setting a higher number of iterations. Now the inside of our miniature Mandelbrot is clearer, but it would be clearer still if we changed the colors. That's better. We can now make out the detail of the small Mandelbrot without difficulty. We will zoom in again to look at the tip. The tip is made from thousands of tiny filaments branching off from the miniature Mandelbrot. We will magnify one of the three-way junctions near to the tip. Again, the picture is a little hazy, so we will change the colors to improve this. Now we can see a picture similar to the three-way junction we saw near the beginning of our journey. Small dots surrounded by clusters of filaments, all connected together in a line. We will look at one of these dots a little closer. What we find at the center of this junction is a strange object which looks rather like two single-celled organisms with a dot in between. We will have to investigate this further. Now we can see that each of the thin cell shapes we saw before is in fact made up of two cells and a dot itself. Each of these cells is similarly subdivided. The Mandelbrot set is full of these examples of fractal self-similarity. We will leave the cells now and zoom in on the dot. The dot has now revealed itself to be a beautiful four-pointed star, quite unlike anything we have seen previously. Let's magnify this star. Now the long, thin, single-cell shapes are back, four of them surrounding another central dot. Keeping on course, we will zoom into the center. Now there are 8 thin cells surrounding a central black circle. Once more we will magnify the central portion of the screen. The central circle is slightly oval in shape and does not have a smooth surface. Let's increase the accuracy level once more. And so we end on another miniature Mandelbrot, as accurate and complex as the original, but microscopic in comparison. To reach this stage, we have magnified the original picture 2,089 billion times. If we now scale up the original Mandelbrot to the same magnification, how long would the complete picture be? Well, if we place the Sun at the tip, then all the planets up to and including Jupiter would be contained within the set. Now you have followed our voyage, why not try one of your own? Each journey is different, and if you go far enough, you will almost certainly view fractal images never before seen by man. Select the Mandelbrot program from the fractal generators to start your voyage. There is fractal structure in almost everything in nature, from the largest spiral galaxies to the smallest snowflake. Here are a few pictures that show some of nature's fractal beauty. No one can deny that fractal images such as this are beautiful, but the question has to be asked, is it really art? Here are some definitions of the word art from several dictionaries. According to the Collins Dictionary, the creation of a work of beauty is art. There seems to be no argument that many fractal pictures are strikingly beautiful. There is no mention in the definition that generation of pictures by computer excludes them from being art. In order to produce plots such as you see on this disc, human skill has been exercised to program the computer and display the pictures. All definitions agree that such skill is a prerequisite. The Oxford Dictionary even mentions technical skill as being a component of art, and there is no doubt that this is present in abundance in the production of fractal pictures by computer. After the picture has been generated, artistic skill can be further deployed to determine the colors to be used in the display. The palette used will have a profound effect on the final picture. For instance, here is a set of variations on color only. The picture elements remain the same throughout. Notice how changing the colors affects the mood of the picture. It is sometimes difficult to imagine that they all derive from the same Mandelbrot plot. Artistic skill is also used to select areas of a plot to be turned into a picture. Here is an original fractal plot as first generated. It might look better if only one side is used. So we will redraw one side only. The end bulb looks the most interesting, so we concentrate on that. Now the picture is rotated, the outer areas are removed and the rest left entirely alone, apart from changing the palette. This is the result. What is it? It looks like a lamp. But that's not all. As before, let's change the palette and see what happens. Something quite different. Is it a decanter? It doesn't matter. Each observer might see something different, but the effect is pleasing. It is art.